Welcome to this session. Today we are going to discuss the adjacency matrix, incident matrix and path matrix. So here to represent any graph into the matrix form. The matrix forms are commonly used to represent graphs for computer processing. There are many number of matrices which one can associate with any graph. Here we shall discuss adjacency matrix and incident matrix. What is meant by a adjacency matrix? And here the adjacency matrix while we are going to consider for the undirected graphs as well as the directed graphs. Now we are going to concentrate for undirected graphs. So for the undirected graph, how we are going to represent the adjacency matrix? So here, any graph is given. The adjacency matrix of the graph G, which is having n vertices, and there is no parallel edges, and of n by n matrix can be obtained by like this. A is a matrix of n by n. So here we are going to consider Aij, that means ith row, jth column. Ith row, jth column. We are going to keep 1 if there is an edge between ith and jth vertices. Ith to jth vertex, if there is an edge will be there, then the corresponding ith row, jth column position is 1. Otherwise, it will be 0. So here, we are going to consider first a simple graph, afterwards a pseudograph, that means which is consisting self loops as well as parallel edges. So here, this is the way that we are going to represent the adjacency matrix of the given graph. So here, for a graph, the adjacency matrix based on ordering chosen the vertices. See, there are n vertices will be there. Then we can choose in n factorial different ways of these n number of vertices. So subsequently there are many as n factorial different adjacency matrix for the given graph, for a graph which is having n vertices. So there are n factorial different ordering of n vertices. So let us, we are going to discuss by an example. So let us consider the adjacency matrix of a graph. Let us say, I am just considering one graph. So let us say it is having 4 vertices. Let us say V1, V2, V3 and V4, which is having 4 vertices. So now let us, I am just connecting in this way. Now let us, I am just taking like this. So it is a simple graph. So for this simple graph, how we are going to represent the adjacency matrix? So the adjacency matrix, I am going to take, let it be the graph adjacency matrix, simple graph, let us say it is Z. Then adjacency matrix of graph G is. So which is having 4 vertices. So I am going to consider V1, V2, V3, V4. Let us say the 4 vertices as representing as the rows, and the columns also I am going to take in the same manner. V1, V2, V3, V4. So here the graph, this is a first row, first column, and the graph does not having a self loop, because it is a simple. So I am not going to concentrate. I am not going to consider the degree of this. So now there is no edge. So I am taking it as 0. Now V1 to V2, there is an edge. So the corresponding position we will take it as 1. And V1 to V3, there is an edge. V1 to V3, there is an edge. So I am taking 1. V1 to V4, there is an edge. So I am corresponding position, first row, 4th column. I am just taking as 1. And similarly, V2 to V1, there is an edge, and V2 to V3 there is an edge. V1 to V2 to V1 there is an edge. V2 to V3 there is an edge, and the remaining there are no edges. There are no edges. Now V3, if I am going to consider, there are edges from V3 to V1, V2, V1, V2, V4. So I am going to consider, so V1 there is an edge, and V2 there is an edge, V3 there is no edge, and V4 there is an edge. And similarly from V4, V1 and V3 there are edges, V1 and V3 there are edges, and the remaining there are no edges. So I am going to consider in this manner. So here, see, observe this is a simple graph. There is no diagonal elements if I am going to consider. All diagonal elements are zeros. All diagonal elements are zeros. So if it does not having a self loop, let us go for, see, this is a 4 vertices it is having. So I am going to get 4 by 4 matrix. I am going to get a 4 by 4 matrix. Similarly, if I am going to consider another graph, let us say I am just taking V1 and next V2 and next V3. Let us, it is having 3 vertices, and I am going to consider a pseudograph. I am going to consider a pseudograph. So here V2 to V2 there is a self loop, and next V2 to V3 there are multiple edges. There are multiple edges. So I am going to consider, here it is a pseudograph. Pseudograph. So while if I am going to consider this, then what is the adjacency of this matrix? So adjacency of the matrix, let us say G1, the pseudograph G1, so which is having 3 vertices. Let us, I am going to consider V1, V2, V3, and then here also V1, V2, V3. Now let us go for this. So V1 to, there is an edge V1 to V2. V1 to V2 there is an edge. So I am just keeping 1. And V1 to V1 there is no edge. V1 to V3 there is no edge. Similarly V2 to V2, V2 to V1 it is an edge. V2 to V2 itself there is an edge. So I am going to consider 1. V2 to V3, V2 to V3, there are multiple edges are there. So here V1 to V2 to V3, there are multiple edges are there. So multiple, how many number of edges? There are 2 edges will be there. So I am considering it as 2. And next V3 to V1 there is no edge, and V3 to V2, so 2 edges are reaching to that, and V3 to V3 there is no edge from V3 to V3. So this is the adjacency matrix for the pseudograph. Let us go for, I am going to consider in whenever adjacency matrix will be given, then how to construct a graph. So for that, let us go for the adjacency matrix. Just we are going to consider 0, 1, 1, 0, and the next 1, 0, 0, 1, and the next 1, 0, 0, 1, and the next 0, 1, 1, 0. Let us, I am going to consider one matrix. It's a 4 by 4 matrix. Let us, I am going to consider the vertices. These are the 4 by 4 matrix. So it is related to a graph which is having a 4 vertices. And observe all the diagonal elements are 0. So we are going to get a simple graph. So let us say V1, V2, V3 and V4. And similarly here V1, V2, V3, V4. So I am going to consider the graph corresponding. This is a adjacency matrix is given. So adjacency matrix of let us say adjacency matrix, and the matrix we are going to call it as let us say M is the adjacency matrix. So for this, the corresponding diagram, let us say I am just taking V1 and next V2 and next V3 and next V4 I have to consider in any manner that we have to consider. So V1 to V2 there is an edge. V1 to V3 there is an edge. First row is over, next second row. V2 to V1 is an edge, and V2 to V4 is an edge. And next third one is V3 to V1 there is an edge, and V3 to V4, there is an edge. Let us just consider like this. And V3 to V4 there is an edge. And now go for V4. V4 to V2 already there, V4 to V3 already there. So this is the graph corresponding to this adjacency matrix. And now let us go for the another pseudo graph. I am going to consider, let us say the vertices are, I am just considering A, B, then C, then it is D. Then another pseudo graph I am just taking. It is having multiple edges as well as self loops. Let us take, I am just concentrating on this. Let us say it is having a self loop, and then it is having two edges. Let us say to D, and D to B there is an edge, and D to A there is a multiple edges. Let us consider, I am taking this graph. Now here for this is having four vertices. So the corresponding graph is M1 and the corresponding graph is Z1 I have to consider. Then, this is graph Z1 and the corresponding adjacency matrix we are going to take it as M1. Then, so it is having four vertices. Let us say the vertices are A, B, C, D. A, B, C, D. Then rows also A, B, columns also A, B, C, D. Rows also A, B, C, D. Now, from A to A, there is no edge. A to B, so here three edges are passing. 1, 2, 3, three edges from A to B. And A to C, there is no edge. And A to D, there are two edges. Similarly, B to A, three edges. B to B, there is no edge. And B to C, there is an edge. And B to D, there is an edge. And next, similarly, C to A, there is no edge. C to B, there is an edge. And C to C is also having one edge. C to C is also having one edge. And next, C to D, there are two edges. And next, D to A, two edges. And D to B, one edge. D to C, two edges. And D to D, there is no edge. So this is the adjacency matrix for the pseudograph G1. So now this is related to the adjacency matrices. Now among all these things what you are observing, so based on that some of the observation related to the adjacency matrix. So here the matrix is symmetric. Whenever Aij is equals to Aji. Suppose if I am going to consider here, so here it is not a symmetric because first row or first columns are same, and next here and next if I am going to take this transpose of this matrix, so I am going to get 1 0 0 of T and then 1 0 0 T. And what about this? Let us say first row third row first column, then second row first column. So it is and next see here second row fourth row second column, and third row fourth column, and fourth row third column. So observe this M transpose if I am going to consider, then what I am going to get? 0 1 1 0. Then next another one is 1 0 0 1. Next 1 0 0 1. Next 0 1 1 0. See, this is whatever the matrix if I am taking, then the transpose is also same. So I can say that this is a symmetric. Or ith row jth column element is which is having jth row to ith column, then it is a symmetric matrix. So that is here saying a symmetric matrix that we are going to obtain if Aij is equals to Aji. Aji. Next, the loops, the entries along the principal diagonal of A, all are zeros if and only if the graph does not have the self loops. Does not have self loop. If it is having a self loop, then corresponding position is 1. So here observe this. See here, these are all diagonal elements. All the diagonal elements are zeros. So the corresponding graph, there should not be any self loop. There should not be any self loop. If suppose any self loop is there, then the corresponding position C to C, there will be a 1. There will be 1. And next, the graph is simple. The graph is simple. That means it does not have self loops and parallel edges. Then the degree of a vertex, the number of ones in the corresponding row as well as the corresponding column. So suppose if I am going to consider, what is if it is a graph is simple, this is a simple graph. So if I am going to consider what is the sum of the degrees of all vertices or the sum of this. So this is nothing but 2. This is equals to 2. And this is equals to 2. And this is equals to 2. Similarly, we can say that this is 2, this is 2, column is also. So what it represents, the V1 vertex degree is 2. V2 vertex degree is 2. V3 vertex degree is 2. And V4 vertex degree is 2. That means if we are going to consider it, the graph is a simple graph, then the degree of the vertex of the the number of ones will be there corresponding row as well as the column. Then suppose whenever the matrix A is given the adjacency matrix of some order, then A square we are going to calculate, that is nothing but A into A, we are going to calculate. Then see A square we are going to calculate, A cube we are going to calculate like this. Then A power m or A power 2, let us say, is the number of paths of length 2. From the vertex Vi to Vj. If I comma jth position, any element will be there that is equals to 1, then there is a path length. There is a path from V1 vertex to Vj vertex or V1 vertex to V2 vertex of length is 2. So like that, suppose A to the power of m, if you are going to calculate the corresponding I comma jth position, if it is equals to 1, then the vertex Vi to Vj, there is a path of length is m. So these are the some observations regarding the adjacency matrix. Now we move for the next adjacency matrix for the directed graph. So far we discussed for undirected graph and this is for directed graph. So the directed graph in the same way that we are going to calculate. So here Aij is equals to 1 if there is a directed edge. See, undirected graph will be there. Simply we are going to take like this, undirected graph. There is an edge. And whenever if I am going to consider a directed graph, I am going to specify the directed edge. Whenever there is a directed edge from Vi to Vj, then the corresponding position we can take it as 1. Otherwise, there will be a 0. V1 to V2, Vi to V2j, Vi ith row, jth column, we are going to keep it as 1. And jth row, ith column, we are not going to keep it as 1. Okay, because there is only one directed edge will be there. So it is, some of the observations which is similar to the previous one. A is not necessarily symmetric. Since there is an edge from Vi to Vj, but there is no edge from Vj to Vi. If there is an edge, no problem. If there are edges like this, and when one vertex edge is moving to another vertex, and from their vertex to another edge is directed edge is coming to that, then we can get the symmetric matrix. But it is not necessary. a symmetric matrix whenever there is a edge from Vi to Vj, and when there is a no edge from Vj to Vi. If there is an edge, then in all the cases of vertices, then we are going to get a symmetric matrix. Okay. Then the sum of the, okay, before that, we are going to solve one of our problems. Based on that, we are going to discuss the observations. So here, we are going to concentrate on the directed graph. Let us just consider a simple graph. So let us say V1, V2, and next V3, then it is V4. So now, we are just concentrating one directed edge. Let us say like this. Then I have to consider the directions. Now here, this is the graph, directed graph. Then the adjacency matrix of G is, so here also V1, V2, V3, V4, and then here V1, V2, V3, V4. V1 to V2 there is an edge. V1 to V2 there is an edge. Next V1 to V3 there is an edge. See, edge is moving from V1 to V2, V1 to V3. The remaining there are no edges, so I am just keeping the remaining all zeros. Now V2 to V3 there is an edge. V2 to V3 there is an edge. V2 to V1 there is no edge. So the remaining are I am just keeping as 0. And V3 to V1, V3 if I am going to consider, so V3 to V4 only one edge. V3 to V4, the remaining there is no edges. And next V4 to V1 there is an edge. V4 to V1 there is an edge, and the remaining are not edges. So this is the adjacency matrix to the directed graph. So here, this is not necessarily a symmetric. See here, I am not going to get any 1 because V1 to V2 is there is an edge, and V2 to V1 there is no edge. So I am not going to get a symmetric matrix at this instance. Okay. So let us. This is related to the. Suppose if I am going to consider one adjacency matrix is given for the directed graph, then suppose if you are going to construct the corresponding graph. So it is given as 0, 0, 1, 1, and 0, 0, 1, 0, then 1, 1, 0, 1, then 3 ones, and there is 0. Suppose this is given, adjacency matrix is given. Now we are going to find out its corresponding directed graph. So here it is having 4 vertices. Let us, I am going to consider V1, and next V2, next V3, next V4. Let us take the 4 vertices in any manner we are going to consider. So V1 to V3, V1 to V3, V1 to V4, there are edges. V1 to V3 and V1 to V4, there are edges. The first row is over. Then the second row, V2 to V3, there is an edge. V2 to V3, there is an edge. Second row is over. Now, V1 to V1, there is an edge. V1 to V1, there is an edge. V1 to, this is V1 to V1, there is an edge. Next, V1 to V2, there is an edge. And next, directed edge. Next, V1 to V3, V1 to V, what about this? Sorry, this is a V3. I'm not going to consider this as a V1. Then it is V3 to V1. See here, third one is V3 to V1. V3 to V1, there is an edge. V3 to V2, there is an edge. V3 to V2, there is an edge. And V3 to V4, there is an edge. Now V4. V4 to V1, there is an edge. V4 to V2 there is an edge. Then V4 to V3 there is an edge. V4 to V3 there is an edge, like this. So this is the directed graph of the given adjacency matrix. So here, whenever there are, if you are finding this adjacency matrix and the corresponding graphs, some of the observations already we discussed this. Sum of any column of A equal to the number of arcs directed towards Vj. Directed towards Vj. That means if we are going to consider, see here, any column. So here I am going to consider this matrix. So the column is 1. So 1 is nothing but one edge is moving. One directed edge will be there to the vertex V1. And similarly, one directed edge is moving towards V2. Towards V2. And here there are two directed edges are moving to V3. V3 here it is and here it is. And V4 only one directed edge moves towards V4. Towards V4. So this is the, so that is the observation. So that shows this is this. And some of the entries in ith row is equal to the sum of the arcs directed away from this. See here it is a column we are going to discuss and this is row wise we are going to discuss. So what is that? If I am going to consider what is the sum of this? So it is nothing but 2. So two directed edges are passing from that word, are moving away from that vertex. So this is one edge and this is another edge. So if I am considering from V2, only one directed edge is leaving that. So V2 is one directed edge is leaving that. And V3, one directed edge is leaving. So this is a undirected edge. V4, one directed edge is leaving. V4 also one directed edge. So this is just we are going to give, this is the column wise and this is the row wise. And similarly, if I am going to calculate A is any adjacency matrix and A square if I am going to calculate any particular element, if it is 1 will be there. Then this is the first row, second column if it is there. Then V1 to Vj, V1 to V2, there is a path of length 2. There is a path of length 2 which is similar to the undirected graphs. Now let us go for the incidence matrix. So now the incidence matrix, what we discussed only two types of matrices. So one is a adjacency, another one is a incident matrix. Now let us go for the incident matrix. So what is the incident matrix for undirected graph as well as the directed graphs? So here also, here the vertices and the edges. The matrix relates vertices and the edges. Vertices and the edges. Suppose any one vertex, there are edges, let us say E1, E2 and E3. Let us, I am just taking. Then here, earlier the adjacency matrix is vertex to vertex. We are going to say that any edge will be there or not. So this is a matrix for vertex to edges. Vertex to edges. Whenever there is an edge from the vertex Vi, Ej is the vertex. Ej is the vertex passing through the vertex Vi. Then the corresponding position we have to take it as 1. Otherwise we are going to consider it as 0. Whenever, see here, E1 is passing through that. So V1 I am going to take like this. And the corresponding edges like the E2, E3. Then E4, let us say there are 4 edges will be there in that graph. So here V1 is passing, then I am just taking the corresponding position as 1. V2 is also passing. V3 is also passing. V1 is not there. Then I am going to take it as 0. I am going to take it as 0. So like that we are going to construct the incidence matrix. The earlier one is adjacency matrix. Now we are going to discuss the incidence matrix. Now we are going to take the examples of the incidence matrix. So here let us consider, I am just taking one example. Let us here the same way, whatever earlier we discussed, in the same we are going to take a undirected graph with 4 vertices. Let us having, this is E1 edge, and this is E2 edge, and this is E3 edge, and this is E4 edge, and this is E5 edge. Now the corresponding matrix is incidence matrix. So here I am just considering whatever the vertices which the graph is having, those vertices we are going to consider it as row wise, and whatever the columns will be there, the corresponding columns we have to consider column wise. So now V1, if I am considering, how many edges are moving from V1? E1, E4, E5. E1, E4, E5. The remaining zeros. Then V2, if I am considering E1, E2, E1, E2, the remaining are not incident to that vertex. Then V3, if I am considering E2, E3, E5. So E2, E3, E5 are the incident edges. Next, V4, if I am considering E3, E4, E3, E4, then whatever the edges are passing through that vertex, then the corresponding edges we are going to keep it as 1, otherwise it will be 0. Otherwise it is 0. Suppose V4, there is E1 is a edge is not incident to this. That means E1 is not passing through that vertex. So I am not going to consider it will be 0. It will be 0. So this is the for a simple graph. Suppose if I am going to consider any pseudo graph or anything, let us I am going to consider in another example. Let us say V1 and there is an edge. Let us say this is E1 and then another one is V2 and we are going to consider edges. Let us take E2 and E3. Then I have to consider V4, another vertex, and next V3, and let us go, I am going to for another vertex V4, and which is having, so what is E3 will be there and E4 will be there. Let us, I am going to consider then V5, so edge is E5 I am going to consider, then edge E6 will be there, then edge E7 will be there, and of course if you want to construct, let us say E8. So this is a pseudograph will be there. So for this the adjacency matrix is, so here V1, V2, V3, V4 and V5. Then how many edges it is having? E1, E2, E3, E4, E5, E6, E7, E8. So now this is a V1 if I am considering. So it is having how many E1 is there and next E2 is there, E3 is there. That's all, and the remaining are not there. So not incident to that vertex. So zeros. And V2 if I am considering E2, E3, E2, E3, and V2 if I am considering E4, E6, E7, E4, E4, E6, E7, the remaining are zeros. And if I am considering vertex V3, 3, so E4 and E5, the remaining all are zeros. Like this. V3 if I am considering, this is for V3, and V4 if I am considering, so V4 is E7 and E8. The remaining things are zeros. Only 2 edges are incident to that vertex. So then 1, 1. Then V5 if I am considering V5. So where is the vertex V5, V1, V2, V3 and V4, V5. This is V5. So E5 and E6. E5 and E6. The remaining are zeros. So this is the incidence matrix for the pseudo graph which is given as this G1 pseudo graph. For that the corresponding incident matrix is this. Now go for the next one for the directed graph. So this is incidence matrix for the undirected graph. Now this is the directed graph. So here in the same way that the incidence matrix is having 1 in ith jth position, ith row jth position, whenever there is a arc j directed away from the vertex vi, that means I can say that in a similar way, from vertex vi there is a directed edge towards vj. If j directed towards the vertex vi, then that will become -1, otherwise 0. So 1 if arc j is directed away from the vertex vi. If directed towards vertex vi, I can take it as -1, and otherwise it will be 0. So in the same way, let us consider one example. So here in the same way, whatever the graphs we have discussed so far, in the same I am just taking V3 and V4. So let us just considering a digraph. So E1, E2, E3, E4 and E5. So here this is the graph, directed graph D1, and its incidence matrices. Let it be A. So what is that? V1, V2, V3, V4, and it is having 5 edges: E1, E2, E3, E4, E5. Now here we are going to consider E5, V1 to E1. This is see here, it is just moving away. Then we are going to consider it as 1 for this E1. And what about E5 is also moving away from that. So E5 I am going to consider as 1. And next E1, E5. What about E4? E4 it is coming into that vertex. E4 I am taking it as -1. And the remaining edges will not coming inside, they are not incident to that vertex. Now V2 if I am considering V2, how many, this is E2 edge is leaving. So the corresponding is 1. And next E1 edge is coming into that vertex. So it is -1. And another one is V2 only 2. So remaining are zeros. Now V3 if I am going to consider V3. So it is moving, E3 is moving away. So the corresponding is 1. E2, E5 are coming into that. Then the remaining are zeros. And next V4 if I am considering, E3 is coming into, V4 is going out. And E3 is coming into. Then the remaining are zeros. So this is the incidence matrix for the given directed graph. So now, what are the So here some of the observations will be there for the undirected graph, incidence matrix. So it is each column of B comprises exactly 2 unit of entries, and a row all zeros corresponding, a row which is having all zeros says that the vertex is isolated vertex, and a row of single unit entry will be there, then it is related to a pendant vertex. Any row, if I am considering all entries are zeros, then it is isolated vertex. A single unit entry will be there, that is a pendant vertex. Then the number of unit entries in I of B is equal to the degree corresponding to the vertex Vi, vertex to Vi, and the permutations of any two rows of B corresponding to a ray-belling of vertices of G. Then two graphs are isomorphic if and only if their corresponding incidence matrices are differ only by permutations of rows and columns. So this is we are going to discuss in the next class, isomorphic and all. If G is a connected graph with n vertices, then the rank of B, then it is a n minus 1. So these are the some observations regarding the incidence matrix for the undirected graph. Now let us go and discuss one more matrix, so which is a path matrix. So here a path matrix, let us G is a graph. Let us the definition is G is a graph. A path matrix is defined between a specific path between the vertices U and V. There are so many paths will be there. So from one vertex to another vertex. So we have to construct the matrix corresponding to that path. So that is known as a path matrix. That means any two vertices, if I am going to consider in a graph, there are multiple paths will be there. We are going to represent all multiple paths in a matrix. That matrix is known as a path matrix. Now, in any graph Z, let us we are going to identify the two vertices. Let those vertices are U and V, two vertices U and V. There are so many paths will be there, and that paths we are going to represent in a matrix, and how we are going to represent that matrix. So here between, let us say it is UV. So path between vertex U and V is defined as Pij, where Pij is equal to 1 if jth edge lies on ith path. We are going to consider it as 1, otherwise it will be 0. Let us consider, we are going to consider one graph. Let us say I am going to consider one graph. Let us say the graph is like this. Then the vertices, let us say I am just considering A, B, C, D, E. Then, so I am just considering some edges. Let us say, what are the edges? Let us say E1, E2 and E3. I am going to consider E3 and E4, E5, E6 and E7. There are 7 edges are there in that graph. Now, I am going to find out what is a path from the vertex A to D. I am going to find out a path matrix from the vertex A to D. From the vertex A to D. So what are the different paths from A to D? A to D. One path is, let us say, P1. P1 is equals to A, and next E3, next D. This is one path. Then the another path is, so this is one path I consider like this. Then the another path is, I'm just taking like this. A, then I'm just considering either this way or that way anyway. 1, then 4, 1, then E, then 4, then D. This is another path. Or I am going to labeling only the edges. So I am going to write this as A to 1, A to 1 edge, along this edge 1, then another one is 4 edge, then D. This is another path. Then P3 is, let us say, A, 2, 5, D. And P4 is, let us, I am considering A, 2, 6, 7, then D. Then D. So there are 4 paths are there. One direct, another one is like this, and another one is like this, and another one is like this. So there is only 4 paths are exist. Now I am going to write the path matrix as P of A comma D, which I am going to represent it as Pij, and what are the paths will be there? P1, P2, P3, P4. Then the edges are, what are the edges? Here I am going to consider the P4 is, let us take a P4 as A2, 2, 6, 7 and D. Then, so what are the edges are? Let us say 1, 2, 3, 4, 5, 6, 7. There are 7 edges will be there. Now, here I am going to consider, first one is path 1 if I am taking, then it is a 3. This edge will be there. The remaining are not there. So I am going to consider it as zeros. Then P2 if I am considering 1, 4 edges are there. 1, 4 edges will be there. The remaining edges will not be there. P3 if I am considering 2, 5 will be there. So the respective position 2, 5 are just taking it as zeros. 2, 5 as 1 and the remaining there is no edge lies on that path. There is no edge lies on that path. So any edge lies on that path, we are taking it as 1, otherwise we will take it as 0. So P4 if I am considering, so 2, 6, 2 is 1 edge 2 is lies and 6 is lies and then 7 is lies and the remaining edges are not lies on the path. Not lies on the paths. So this is the path matrix. This is the path matrix. Similarly, we can find out there is a path matrix from vertex A to D. And similarly, we can consider what are the path matrix from A to C, or what are the path matrix from then B to D. What are the path matrix? What is the path matrix from B to D? So like that, we can find out so many path matrices. So many path matrices from the given graph. So here we are considering the undirected graph for this. So this is the path matrix, how we are going to construct the path matrix. So today's we discussed here what is the adjacency matrix for directed and undirected graph, and what is the incidence matrix for directed and undirected graph, and what is the path matrix and we discussed for the undirected graph. And in the next session we'll be continuing in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.